Hello students, today we shall see the next module which explains about the modeling for analysis. That is, when we are doing the analysis of the tall structure, how the model is to be done, or the modeling of the structure, how it is to be done, and what are the assumptions to be made, and how the analysis is to be carried out. So now first is the building deflects depending upon the loading of the components. So now when the horizontal load is acting, we see that the building gets deflected. So it depends upon the loading, that is whatever loads are acting on different components. So for the analysis, we consider only the main structural elements. So which will be the main structural elements? We consider is the slabs, beams, girder, columns, walls and the cores. So these we consider as the main structural elements, and we do not consider the effects of the non-structural components. So the non-structural elements or the components here will be the, for example, say staircases, partitions or the claddings, etc. So a building's response to the loading will be governed by the what or the which components they will be stressed and how the building deflects. So to identify these main structural elements, we recognize the modes of action, that is different modes of action which are acting. Depending on that, we consider the main structural element and which part of that structural element is contributing to the behavior of the structure. So now this we know that the building will get deflected, the structural elements will be contributing to it. So how the approach is to be done? So the approach to analysis. So the modeling of these tall building structures for analysis is dependent to some extent on the approach as to what approach we consider for the analysis part. So which in turn is related to the type and the size of the structure, and also on the state of design and what stage of design you are considering the analysis. So these modeling of tall buildings will depend upon the how is the approach of the analysis here. So this is divided into say three parts. So first is usually we consider as the approximate analysis, then we have the accurate analysis which will be the final stage, and a hybrid approach is there which is a combination of these two. So now this usually approximate analysis which is there, which is considered at the initial stage or the preliminary stage, we consider the approximate analysis, which will be usually a rapid one, that is you get a fast result for that. And second is a detailed and the accurate analysis. So we have a detailed, we do all the detailing we do, and then we find out what are the accurate values. This will be in the final stage. And next is the hybrid approach. So we shall see these analysis. That is first one, as I said, it is a preliminary analysis. So purpose of this preliminary analysis will be done in the early stages of design. So here what they do is we compare the performances of the alternative proposals. So you may be having different proposals here. So what we do is we compare their performances of the different structure or that structure, the different proposals which are done, we compare their performances and check which will be the ideal one, and then we find out the deflections and the major member forces for the structure. So whatever model or the whatever proposed model you choose it, we find out, this is at the initial stage I am talking about. So we find out what are the deflections and the major member forces which are acting in the structural components. And then later the model, they model it, and the analysis whatever we do, it should be a rapid and a fair one. That is whatever approximations we make and we prepare the model, so it should give us the rapid and should give a fair result for it. So simplifications are adopted and approximations are made for the complex structure. So if the structure is very complex, we make it a simplified version and we make a lot of approximations here to make that complex model a simple one. So now when we make that model a simple one for the approximate analysis in the preliminary stage, the results which are obtained, okay, that is a deflection member force result, they should be within a value of about say 15% of the values of the accurate analysis. That is later further when we go for the accurate analysis, the results should not vary say about say within the limits of 15%. So this is about the preliminary analysis. Next is the intermediate or the final analysis. So now in this intermediate or the final analysis, the accurate results should be obtained. Okay, whatever results are there, they should give the accurate values, and the model which will be prepared, it will be a detailed model. Not like the preliminary model where we make certain approximations and do the modeling. Here, in this case, we should make a detailed model and get the results which should be accurate. And the major modes of action and the interaction, they should be considered. So whatever, where the loading is acting, how the action is taking place, what is the interaction between the beam column. So all that should be considered while doing this modeling, and the reduction in the sizes of the model can be done in here. Then here in this case, the columns, beams and the bracing members, they will be represented by beam elements, while the shear wall core components, they may be represented by membrane elements. So we give the representation of the actual model to the model which we are analyzing. So here also it is given that for symmetric building structure loading, the twisting effect is to be considered and a 3D analysis of the half structure model is to be done. So if the building is symmetric, we go for the half structure and go for 3D analysis, or a 2D analysis of full interactive 2D model can be prepared. So all these we consider for the intermediate and the final analysis, and the detailed report or the detailed analysis of certain parts is to be done. So if a certain part we want to analysis in a deep, so we go for the detailed analysis for certain parts then. Then next we have the assumptions made. So assumptions, what are the assumptions we do when we go for the analysis part? So an attempt to analyze these high-rise buildings, we make certain assumptions for the behavior of the different components and the materials, and even if the sizes and the properties were known here. So simplifying the assumptions are necessary to reduce the problem. That is, whatever model is there, when we do the assumptions and we apply it for during the analysis, it makes the analysis the easier one. So first assumptions what we make are depending on the materials. So the material of the structure and the different structural components, they are considered to be linearly elastic. This is the first assumption we make. So now this assumption will allow the superposition, means we can superimpose the actions and deflections here, and hence we can use a linear method of analysis. So the development of the linear method and their solutions by the computer can be made possible, and large complex problems can be solved here. So here first assumption, material of the structure and the structural components are linearly elastic. Even non-linear methods are, even though we apply these non-linear methods in the analysis, since the high-rise building, linear methods can be applied since we consider it as linearly elastic here. Next is the participating components. So here we consider is only the primary structural components, they participate in the behavior. So for the high-rise structure, we consider is only the primary structural components are considered, their behavior is studied. Whereas the secondary structural components and the non-structural components are assumed to be negligible. Okay, so this is the second assumption. Third assumption is the floor slabs. So we consider that whatever the floor slabs they are there, okay, they are considered to be a rigid in plane. We consider them to be rigid. So this assumption which is there, it causes the vertical members to have the horizontal plane displacement. So what happens, since we consider the slab to be a rigid one, since the horizontal loading is acting, the vertical members, they move horizontally and they cause the displacements at each floor level. So that can be defined in terms of say rigid plane body rotations and the translations of that floor slab there. Then next is negligible stiffnesses. So component stiffnesses, so whatever stiffness of the components, different components, if they have very small value, okay, they can be assumed to be negligible or they are not considered. So this assumption, the use of this assumption should be dependent on the role of that component in the structure. So what component stiffness you are neglecting, it depends what part that component is playing in the structural behavior. Then next is negligible deformations. So whatever deformations are taking place, if they have a very small value, they also can be neglected. So usually they include the shear and the axial deformations of beams. Then next is the cracking. So the effects of cracking in the RC member, that is a reinforced concrete member, due to the flexural tensile stresses. Okay, due to the tensile stresses, they are assumed to be reduced moment of inertia. So they are represented by a reduced moment of inertia. I value is given. So usually the gross inertia of the beams, they are reduced by 50% of their uncracked value, and the gross inertia of the columns are reduced by 80%. So these are the assumptions which we make while doing the analysis part. Now next we shall see how the modeling is to be done when we consider the approximate analysis. So as I said, when we do the approximate analysis, which is in the preliminary design stage for the proposed structure, it should have, that is, it should find out, it should give the structure stiffness and feasibility. Okay, so the preliminary design stage, it of the proposed structures stiffness and hence its feasibility should be found out. Then to estimate the allocations of the external loading between the bends and the detailed bend analysis. So now here that is, these are the we can say this is what we find out from that approximate analysis. So here the estimate of the allocation, so whatever location of the external loading is there between the bends. Bends are nothing but the building blocks which define the shape of the structure, the characteristic of the structure here. So these bends, for detailed bend analysis, when you go for detailed one, it will give, when you go for the detailed analysis, that time we need to find out what is the locations of these loadings on the bends. So it may be a numerical analysis of a simplified. So in the approximately you may have a simplified model, or the analysis may consist of the closed solution leading to the differential equation. So you have a wide range here, maybe a simplified modeling with simple analysis, or it may have the closed solution having the differential equations here. Then these approximations which are made depend on how closely they represent the real structure. So whatever real structure is there, when you do the modeling for that, how closely or how deeply you define all the points from the real structure to the approximate model, that depends. So now first is approximate representation of the bends. Okay, so this is all approximate means we are doing for the preliminary stage here. So now here we see that the approximate representation of the bends we do. So here we can say these are the bends here. Now bends, as I said, it will be the building blocks which will define the shape of the structure. Now this is the actual real structure, and this is the representation of this structure in the analysis, or when you're doing analysis in the software or now we do, this is how we represent the actual real structure. So now here what all we do is the bends which are consisting of the shear walls. So now this is the bend of the structure which is there, which is consisting of shear wall, or it may be a moment resisting frame. Okay, this which is there, you consider that it is a shear wall or a moment resisting frame. It is modeled approximately, okay, provided that the flexural, okay, the flexural and the shear characteristics of this original structure, they are reproduced in this model. So this is the model which we represent here. This is the actual structure and this is the real model here. Sorry, this is the model which is representing this actual structure. So now what it is saying is whether it is a shear wall or it is a moment resisting frame, the flexural and the shear characteristics of this original structure, they should be reproduced in this model. Right? And now here there are two pictures you can see here. Now in the first one, this is axially concentric tall shear wall. So it is a shear wall. They have shown this is a shear wall and it is axially concentric. Here you can see it is axially concentric. Okay, and it is having a uniform region. So this, when it is model, it can be represented by a column. See, this is the column located on the centroidal axis of the wall. So this is the centroidal axis. So it is shown in the model here, centroidal axis of the wall. A column is there. Now this part which is there, as it is seen I1 AS1, here we represent it as I1 AS1. So whatever flexural and the shear area is there, that you represent in the model here. So I2 AS2, I2 AS2, I3 AS3, I3 AS3. So this is divided into three parts. So 1, 2, 3. So 1, 2, 3. So three parts and three representations are done. So this actual structure, it is modeled in the same way by showing a column wherein first part is this is the second part, this is the third part. Okay, this is how we do the or represent the actual model. This is how we do the modeling for this. Now suppose the next is the column segments. They will be assigned to have the inertia and the shear areas of the corresponding regions of the wall. That is what I shown here. So corresponding regions, it is represented here. This region is represented here. This region is represented here. So this is in case when it is axially concentric. Now suppose if the centroidal axis of the wall, it is not concentric. Here you can see in the second picture here, the centroidal axis, this is for this part. For this part, this is the axis and this is the third axis. Now in this case, what they do is the same way columns are represented. That is, this for first part, this is the column along the centroidal axis. Second part, this is the column. Sorry. Then for the third part, this is the column. So now these three columns will be represented. They will be connected by a horizontal rigid arm. So here you can say this is the rigid arm which is connecting this column to the first column. This is the rigid arm which is connecting the third column to the second column. Okay. So this is the case when it is it is not concentric. The centroidal axis is not concentric. So same way here also, whatever inertia and the shear area is there, they have to be represented same way in the model. So here also same I1 AS1, I2 AS2, I3 AS3. Whereas here you will be having the rigid arms. This is next the column which is used to model the wall. Okay, when you are representing the column which will show the wall there, the wall stresses, they will be calculated, okay, by applying the resulting column moment and the shear. So whatever column moment and the shear is there, that will be applied for the wall stresses. Then suppose you have multi-bay rigid frame. So this is the rigid frame which is shown. It is multi-bay, that is, this is one bay, second bay, third bay. So there are multi-bay, many number of bays are there. They can be represented in the model by a single bay here. So you can see here a single bay rigid frame is shown. Then for this representation, what should be the equivalent you can do is the criteria for equivalence. That is the same way when you are representing as a single. The equivalents are that the shear rigidity, that is the racking is these all different stories shear rigidity as defined by the columns and the beams. These columns and the beam shear rigidity, flexural inertias, that is the I value, then the column inertias, that is sum of the column inertias, summation of capital I small I, overall flexural inertias, that is the IG, okay, the G is representing the overall flexural inertia, and the column sectional area at each level, the same as the equivalent single bay frame. So when you are representing this multi-bay frame in a single bay frame, here it is shown, it will be summation of I1 by 2 and the summation of I1 to IG1 GA1. Shear rigidity, the flexural inertia and the column inertias. Okay, so this multi-bay can be represented as single bay also, and the analysis can be continued. Now suppose if it is a rigid frame and also it is a braced one, here you can see the braced frames are there. It may be a single or it may be a multi-bay as shown here. It can be represented by a single column. So here you can see it is represented by a single column model, and the shear area of the analogous column is assigned to provide the same shear rigidity and the racking rigidity of the bend. So whatever these diagonal bracings are there, the bracings, the same shear rigidity and the racking shear rigidity is to be provided here. So you can see IG1, GA1. The flexural inertia of the equivalent column, whatever column we assign it, is assigned to have the same value as the inertia of the column area of the common centroidal or the common centroid in the braced or the rigid frame. So if it is braced rigid frame, it should have the same, that is equivalent, same values as the equivalent column. So now this is just the representation as to show you all when the there is a different structural forms which are there, how they can be modeled and what is the equivalence characteristics we have to consider. So now suppose next is if you have a shear wall, that is here you can see in this first picture two shear walls are there, okay, and they are connected horizontally and vertically by the say beams. These are the beams present, these are the two shear walls or other parts of the structure. Now how they can be represented, how the model can be done for this is, they will be having a wide column. So they'll be having, so this shear wall which is there, it is represented by column 1 here. This is the second column having the same that is inertias and all. You can see I1, AS1. Then here column 2, I2, AS2. Right. Now these that is shear walls, they are represented by the columns, and these beams which are there, okay, in between beams, they will be connected or they will be shown as the rigid arms. So these rigid arms, they will connect these columns to the beams here, okay, between these beams which are there and the column, the shear wall which is represented as the column, they will be connected by this rigid arm here. So here it is shown the column which is placed at the walls centroidal axis and assigned to have the wall inertia and the axial area having rigid arms, okay, these rigid arms that join the column to the beams at each level. So these are the rigid arms which are joining the column to the beams here. Now suppose if you have a non-planar assembly of shear wall, that is they are not in the same plane. So if they are the non-planar assemblies of the shear walls, they form the elevator. So here you can see this is one shear wall, this is other, this is other. So they are non-planar shear walls in this A and B. Now in this what happened? In which the first cases they translate but they do not twist when the lateral loading is acting. That is, they translate, they move about, but they do not twist. Okay, it is shown by a single column. So that can be represented, or equivalent model is shown by a single column which is located at the shear center. So this will be the shear center since it is not in the same plane. So it is located at the shear center on section and assigned the second moment of area. So it will be assigned the second moment of area of core section, right? So here we will be having, since it is not in the same planar, you will be considering is the second moment of area. So you represent it here Ix, Iy. This is in case of the non-planar assemblies of shear walls. Okay. Next, if the structure it is non-planar, okay, as well as if the structure is twisting as well as translating, it is movement is there as well as a twisting is there, then the core as an effective closed box. So this closed box which is shown, okay, then the single column which is there, it will be assigned a torsion constant. So we include the another mode or another constant we have to represent here will be the torsion constant, that is Jz. You can see here Jz is there, Ix, Iy, that is we consider second moment here of areas, and the that is Jz, that is the constant torsion constant. G also should be considered. Okay, when do we consider it is when the structure is twisting as well as translating. Now suppose if the structure is twist and translate, okay, and core walls, and they have also the open shape, okay, the same, wherein it will twist and translate and it is an open shape here, whereas this was a closed one. Then in this case we consider is the warping constant is to be considered in this case. Okay, you have the torsion as well as the warping, which is represented here, you can see. Okay, the representation, that is approximate representation of bending and torsional properties. So it will give the how the bending is done as well as torsion, because it is twisting as well as it is translating. So these models you have to just see how the representation is done. Okay, that is actual structure when it is present, how the representation of this will be done while doing the modeling in the analysis part. So next is the approximate modeling of slabs. This we shall see in the next video. Thank you.